Hello. So today I'm going to be looking at the water cycle and water insecurity topic, and I'm going to be looking under the first inquiry question. The process is operated in the hydrological cycle from global to local, and we're going to be dealing with 5.2c. So this bit here. So if you click on the right Google Doc, we'll go through this bit. So to break down what we've got to do with this, so clearly now if we're looking at the mainly local cycle, or local places, so the local hydrological cycle. So if we just read through 5.3c, so we've got humans disrupt the drainage basin cycle by accelerating processes. So the processes it's talking about is really looking at the flows. So things like evaporation, surface runoff, those flows. It would be useful to have this diagram in one of the textbooks. All the textbooks have this diagram. This is the WAF textbook version, but you can use the Frost textbook or the Dunn textbook. They've all got this, but it's worth having that there because it shows you all the different flows and processes. So the flows or the processes it's referring to really, we're talking about the yellow bits, is what the focus is on, but any disruption to any of the stores as well, because if you change the stores or the flows, sorry, then you've got to change the stores. So disrupt is any change really to the cycle, and these first ones accelerate it. So it's making these flows move faster, and we've got to look at deforestation and changing land use for that. So the focus on that is both disruption and acceleration of processes. The second bit, creating water storage reservoirs or abstracting water, that's really about disrupting the cycle. There are some changes in terms of acceleration of processes, but this is about disrupting the cycle. So if we look at the first bit first, so humans disrupt the drainage basin cycle by accelerating processes, like it says in bold underneath. So be able to both explain how each might influence or accelerate the hydrological cycle. And you may have to assess the importance of these different factors. So assess the importance of deforestation in how humans disrupt the drainage basin cycle. So you'd assess that, its relative importance, compared with the other things on the list, such as changing land use, so over abstraction and so on. There's a few A-level questions there, the type of thing you might face. They're the 6-mark explain questions to begin with. You might be given a figure somewhere to explain the changes on the figure as well to the drainage basin, so it might show deforestation rather than actually state it. Anyway, so if we look at the first one, deforestation, what we've got to look at here is if you chop down trees, in what way will that mainly accelerate and disrupt the natural hydrological cycle in the area? It says in the specification when you look at the top that you need an example for this, and it suggests Amazonia, and it makes sense to use that one because we're going to use it again when we do carbon, and we're looking at the influence of deforestation with climate change and disruption to the water cycle. And it's useful because it's in most of the textbooks as well, so it's easy to find information. But you could use local deforestation as well in a question. Now, the diagram here is from the Frost textbook, which is really useful because it shows the difference between an undisturbed forest and a degraded forest. And then if we combine these ideas with the Amazon rainforest and make it specific, then we've covered all bases. So for this one, what I've done is use that diagram and what's in the textbook to write an explanation of what's going on. Remember, we're focusing on acceleration and disruption, so where it's changed things or made things go faster. This particular place is the diagram's based on Nepal, and just if you wish to, I've digitized a little video there looking at that problem, and if you just go to 5 minutes in and watch the next 3 to 4 minutes, it goes through the problem of deforestation and the impact it's having on water supply downstream in places like Bangladesh, where the deforestation is going on in Nepal, which is in the Himalayan mountain range, and it's affecting rivers like the Ganges, which flow down towards Bangladesh and causing flooding and so on. Anyway, so fundamentally, deforestation does accelerate the local hydrological cycle, so directly linking to the spec. So like it says there, because it reduces, or one reason is it reduces interception. Interception, if you remember, is the rain striking plants before it reaches the ground. So if you've got lots of interception, it slows the water down, like it says here on the diagram, where you've got the drips to the ground slowly. The emphasis being on slowly rather than rainwater striking the ground immediately and then going straight towards the river. Which is there. So rainfall strikes the soil directly or grass near the surface, and it also compacts the soil. So interception slows the water down, and it also avoids soils becoming really compact. And just digressing a little bit, if the soils become compact, it means that infiltration rates will drop. So when the rain hits the ground, it compacts the soil, just like if you imagine you stamping down on an area of soil, and then you pour water on it, the water's less likely to sink in and more of it will flow over the surface. So anyway, the precipitation reaches the ground faster. That means that the ground has less time to absorb that water. It's all about proportion. If you imagine pouring water on the ground from a jug, if you pour it really slowly, the soil will absorb most of it. But if you pour it faster and faster and faster, more and more of that water will flow over the surface rather than sinking into the soil. So if you pour the water really slowly over quite a long period of time, all of the water might infiltrate into the soil. But if you go faster, some of that water will pour over the top of the soil. So this is what this point's getting at here, is it results, if you've got less time for infiltration to happen because you've got less interception, proportionally more of the water will flow over the surface. Just a little caveat to that though, every type of soil has a certain rate of infiltration depending on its situation at the time, because it also depends on how wet it is or saturated it is. But if you've got, for example, a really sandy soil, it will absorb water more quickly. The infiltration will be faster. But regardless of the soil, there'll be a threshold point, which is a key concept, a threshold point of which if you pass, i.e. the rate of rainfall, it will pass a threshold where the soil infiltration is exceeded and it will lead to surface runoff. So if the soil can absorb 2 units of water a second and you're pouring 1 unit of water a second, all of that water will be infiltrated and go into soil moisture for a period of time anyway. If you go above 2 units a second, then any extra will flow over the surface. So if interception is reduced, water hits the ground faster, it means the water's less time to infiltrate, so more of the water will flow over the surface, which is what that's meaning by proportionally more of the water flows over the surface. And that means it will reach the river quicker, because surface runoff is a much faster route to the river than sinking into the soil and flowing slowly through flow within the soil. So if it has to sink in and then flow through the soil, through flow, it's slower, it gets to the river more slowly. So that means the river gets a lot of the rainwater all at once and it increases flood risk. So the lack of interception has knock-on effects, and it increases surface runoff, which then increases flood risk, and the rivers become more erratic. You get higher peaks and troughs in the river level. Also, additionally to that, you've got less trees, which means, or clearly with deforestation, you have less trees, but the trees remove water through their root systems. So if you think about it over time, the soils under trees are likely to be less saturated, if you remove the trees, the soils are more likely to be more saturated or full of water. So if the soils have got more water in them, it means they've less space to absorb any rainwater. And if you imagine the extreme where the soil is completely full of water, then there's no room for any more. So infiltration will stop, and then all the rainfall will become surface runoff. But the wetter the soil is, the slower the infiltration tends to go as it starts to fill up, and all the air spaces start to fill with water. Clearly, that would depend on how deep the soil is as well, and the type of soil you've got, and what time of year you're in. For example, at the end of the summer, where the soils are really dry, you tend to get a lot of water, a lot of room for rainfall. But if you're in February, March, where it's been raining all winter, and in this country, and less evaporation, the soils tend to be full of water. But trees remove that water. So the key point here is if you've got less trees, less water is going to be removed from soil moisture, which means less room for further infiltration. On top of all of that, then, that also means there's less transpiration, which is another process, which means less condensation and less precipitation. You could explain that further in the Amazon, but the key idea here is, as we've deforested the Amazon, less trees means less transpiration, which means less water's entering the atmosphere, which has lowered the amount of cloud formation, which then has reduced the amount of rainfall. And in the rainforest margins, where it's drier anyway, this is becoming a problem, and they're getting more forest fires as well. So it's disrupting all that system, and there's a direct link there to the carbon cycle as well, because it's encouraging more forest fires, particularly in the drier seasons. Also, indirectly, this is slightly off the slightly indirect point, but if you've got less roots because the trees have gone, you get more soil erosion, and that's going to reduce how much water the soil can store. So it saturates more easily. Once it's saturated, any more rain that falls on top of that soil then flows over the surface. It's a bit like soil compaction. Like we talked about earlier, if the rain falls directly onto the soil, it compacts it. Also, if you put grazing animals in the place of those trees, they will also compact the soil, which means more surface runoff because you seal all the gaps or the air spaces and the porous spaces where the water would have infiltrated. So when you look at this diagram here and you compare it with this diagram, what you're trying to show is how all these things will change. So for example, if you reduce infiltration by soil compaction, it means you're going to get more water sat on the surface, which is going to lead to more surface runoff. And that's going to go then straight to the channel store quicker, which is going to cause higher peaks and troughs. If you have less infiltration for all those reasons we said, if you have less roots in the soil, you have less ways into the soil for the water because the roots break the soil up. Even things like under forests in this country, you tend to get more worms, more detritivores. They burrow holes in the soil. They create drainage, which means more infiltration. So more of the water goes into soil storage. You remove the trees, that stops happening. We've talked about vegetation. If you remove the trees, you have less water taken out of the soil back up to transpiration. So it's just a case of following the logic of this diagram to show how those processes will change if you remove the trees, which is what this has started to do. And then a similar thing is true of land use. Now I would write a paragraph a little bit like this for land use changes. Now clearly, if you're changing a forest area to cattle farming, you can apply what you've just said. And just before we go on to land use, just mention as well, you really need a place for this. So I would have a look at your two textbooks, Frost and Hodder. They both do the Amazon basin, so they look specifically at what's going on in the Amazon. So you do need to have a little bit about the Amazon there. And also you've got the Frost textbook. Let's go back a little bit. It does human disruption of the water cycle in the Amazon as well. So make sure you've got an idea of what's going on in a particular place, and it makes sense, as I said before, to do the Amazon. There's also some notes here on Bangladesh if you want them. And don't forget the Nepal one, so you've got plenty of places to choose from. You can do more than one if you wish. Last little bit, there's some synoptic links or links between other topics here. If you wanted to take this a bit further, you could read about the ENSO cycles, which you will be doing when you do carbon, and it's good to make the link now anyway. I'm looking at how these affect rainfall in the region, particularly in the Amazon, and they do affect rainfall in places like Brazil, and when you get dry years because of ENSO, or wet years, it's going to affect this system as well, and it's going to combine with the deforestation. You could also bring in climate change, because obviously as climate change is starting to impact on places like the Amazon, it's been seen to get drier, and as it gets drier, as well as causing deforestation, the two together are making it even drier because they're combining, which is increasing forest fires, which is then further increasing climate change in a positive feedback cycle. You also need to know about flood risk later on in the topic, and one of the key ways of increasing flood risk, and because it disrupts what we've just been talking about, the hydrological system, because you need to know about it later, on page 52 of your Frost textbook, it does talk about increasing flood risk due to deforestation. So you can link all of that together if you wanted to, if you're feeling particularly enthusiastic. But it's all stuff you'll have to do later anyway. So when we're looking at changing land use, you can look at the land use changes, and part of that could be deforestation, but you could also consider things like urbanization. The key thing with most of the land use changes is they reduce infiltration rates. So if you build houses and tarmac and roads, you stop water sinking into the soil. Infiltration stops, so the water goes straight over the surface and straight to the rivers, and it increases flood risk. This is a major problem in our urban areas. There's a local example here of where they're building homes. This is around the back of Pinderfields Hospital in this green area, and those homes, instead of having fields which would have a reasonable infiltration rate, you put tarmac on that, it will stop those fields absorbing that water. So soil moisture storage will go down, infiltration rate will have decreased, and the water will go straight over the surface to the river. It's accelerating the processes and causing flood risk at the same time. So I suggest you write a similar paragraph to the one on deforestation on changing land use. And again, there's a few examples in your textbook on that as well. But urbanization and changing forests to cattle ranching is probably the best way forward on that. If you have a look at Frost, page 31, there's some stuff on that too. Just find that here. So you've got urbanization there. It's always nice to use a local example like the one in Wakefield we've just seen there. Right, the last two, new water storage. This is called really about reservoirs and building great big reservoirs in areas. So you dam a river by putting a wall across a river. The water builds up behind the wall or the dam, and then that's released in a controlled way. The advantage of that is in times of when you've got lots of water, you can store it, and when it's dry, you can let it go. But unfortunately, at the same time, that can disrupt the cycles because, for example, if you create a huge lake, when the sun shines on that, you're going to get huge amounts of evaporation. The Aswan High Dam is a really good example of that. And again, it's a good example to use that because you need to look at conflicts later with dams along the River Nile. So that's not a bad one to use for that as well. So it's good to get to know that one. There's some notes in the textbook on that, so I'm going to leave you to that. But the key idea is it can change evaporation rates, so you lose more water to the local system. So it can dry the area out because you have less water in total left because of the evaporation. And it also can control the water flow down the river. And the last one, which I've done a little bit more for you, is water abstraction. Now, the textbooks tend to focus on groundwater abstraction, but both of them do that one, the Frost and Hodder. But the river water abstractions is perfectly valid too. This is all about removing water, and if you remove it faster than it's replaced, it becomes unsustainable, like it says there. And if you cross a certain threshold and the river levels drop too low and the groundwater starts to drop, it's going to have ecological damage. It's going to cause ecological damage. Now, the orange words are the key concepts, which, if you remember, I'll just show you where they are again. If you click on key concepts there, got a list of them. They're in your exam specification as well, but the examiners want you to use these. So we have the sustainability one there, and we've got threshold, where you go across a certain point and it causes damage. So most ecosystems have a certain level of resilience, and then you get to a certain point, and then you get major damage, and that's crossing a threshold. Resilience itself is another word to use in that. So keep trying to use those words. Anyway, so abstracting water, I've given you and left some notes here, but it's mainly for agriculture and industry, like we said, and it's all about if the abstraction's faster than replacement. So if you're taking more than's being replaced, over time, that becomes unsustainable. So like it says there, it fundamentally disrupts because it is unsustainable to abstract more water than replacement rates. This is a particular problem if you've got fossilized water, which is not being replaced at all, and it's non-renewable. If you go back to your notes from before, there's non-renewable fossilized stores. Once it's gone, and that's non-renewable, and these places can become polluted and you can start to run out, and then we need to find another option. So it's going to, anyway, if you do that, you're going to disrupt processes, which is what we're focusing on here. So it's going to reduce groundwater flow. So if we go back to our diagram of the hydrocycle, we're talking about this groundwater or base flow down here. If you keep taking water out of groundwater, eventually the level of groundwater will drop. If you imagine deep in underground, well, not always deep underground, but underground, the zone of saturated bedrock and soil, depending on how deep you go, that is groundwater storage. And what I mean by saturated is all the air spaces have gone. If you were to dig a hole into that, so you dig a hole or a well into that, it will just fill up with water. Like if you're on a beach and you dig deep enough, you go past the groundwater, you go past the water table into groundwater. Any point underneath the water table, water will just pour in from the sides and it will fill it up. The water table marks the top of groundwater. So if you keep taking water out of here and abstracting it for agriculture and industry, that water table drops. Now, one of the consequences of that is the water table, the top of it, also provides the base flow for rivers. So if rivers are in the under the water table, in dry periods, it's the base flow which maintains the rivers. So dropping the water table can have quite serious consequences there. And not to mention, if you're relying on that water table and you're digging wells into it, if it starts to drop, also if you pollute it as well, it's going to cause all sorts of problems for people and agriculture and the people relying on it. So the water table reduces and also river levels will drop. Also, if you directly abstract from rivers, that will also cause river levels to drop. And if you imagine all the ecology which will be disrupted there, then you can do a little bit of research on that. You won't need very much for the exam, but there's no harm in looking at some of the impacts of dropping river levels and changing river flow on things like the fish communities and the aquatic life. Now, it's really significant this in North China because they're abstracting so much, and every year they're increasing the abstraction rate by 2.5 billion meters cubed per year. And this is really significant because the area is already dry in North China, and it's got dense populations, and that same water provides 70% of all the drinking water in the area. And because of this abstraction, the water table's fallen by a meter since 1974. Now, you could then also look at other examples. Now, I would probably take a river examples or other abstraction from rivers as well, and groundwater. And the Aral Sea is a brilliant example of this. Now, the Hodder textbook, in this section here, I can't draw on this, but this section here talks about the Aral Sea just in there. And the Aral Sea, if you look it up, or even just do an image search, you'll see it's been a really, like it says, a disaster, where the The sea has just shrunk and shrunk. And this article, obviously, you might read this if you're feeling particularly enthusiastic, but it talks about all the problems in and around the Aral Sea and the issues it's caused for the economy and the local fishing community and so on. But this sea has been really badly damaged by over abstraction. And you've got two rivers. And the problem being with this is the cotton farming in the Soviet Union has taken, and there's also cereal farming as well in the area, has taken huge amounts of water out of this area and out of the rivers for irrigation. Irrigation is just the artificial watering of crops. And in doing so, they've reduced the inflow to the Aral Sea. So the rivers that flow into the Aral Sea, there's less water going in, which is then causing it to shrink. And this graph really sums it up. So if you go back to 1911 to 1960, you've got the river inflow, net evaporation, you've got net groundwater inflow, so the groundwater pouring in as well, and you've got a slight surplus. That's pretty stable. But as time's gone on, you'll notice that net evaporation's gone up. Net evaporation actually hasn't gone up. It's just gone up relative to the inflow. So it's the balance between the two. So river inflow has been going down due to the irrigation upstream. Evaporation stayed much higher, which has led to a constant deficit. If you think about it, there is a bit of a negative feedback system going on here, whereas the net evaporation has been going down as the sea shrunk because there's less water there to evaporate. And it could have eventually become an equilibrium, but because we keep taking so much, you can see the balance has not been found because we're constantly taking more, or taking so much out of the rivers that it means that evaporation is constantly higher than the river water entering the sea. So you end up with a constant deficit, and even if the deficit's a little bit smaller, it still means it's shrinking. And if you just look up photographs of the Aral Sea disaster, you'll see it's literally now turned into a desert, a lot of it. And it's completely wiped out the aquatic life and so on, as well as the fishing industry in the area. And some real hardship now because of that. So that's a really good example of where we've over-abstracted river water for irrigation and agricultural purposes, and it's completely destroyed an environment. And it's only recently they started to try and improve the situation using some management techniques and damming certain areas and trying to link two sections of the sea, because it's kind of divided into two different water bodies now, rather than just the one sea it was once. So going back to the beginning of this, as long as you can clearly explain how humans disrupt the drainage basin cycle, and make sure you can talk about the ones mentioned here, and maybe assess how serious these are by some of using the examples we've looked at as well, then you're done. A lot of the notes are done for you. Some of them you'll have to do a little bit more yourself. So deforestation, it's just a case of making sure you understand that one. Changing land use we've gone through. It's just a case of writing something up which fully explains how it might disrupt the water cycle. New water storage, again, it's we've discussed it. You've got the information you need there. And don't forget the textbook, particularly the Frost one's quite good on that, with the table which summarises those changes. Remember that, focus on the disruption there and possible acceleration up to a point. Abstracting water, I've done a fair chunk of that for you, but I would definitely have a look at the Aral Sea for that and pull that together so you can really explain how abstracting water may disrupt the processes. Okay.